August 1923, Cumbres Pass, Colorado. At 10,000 feet above sea level, the morning air hung thin and cold as the Rio Grande Southern's newest acquisition labored up a fought grade that would have torn lesser machines apart. The mallet-type articulated locomotive, all 285,000 pounds of it, flexed through curves that seemed to defy the laws of physics, its front engine pivoting independently while the rear drivers clawed at rails that clung to mountainsides by little more than engineering audacity and blasted granite. Steam hissed from every valve as fireman Jake Morrison shoveled Colorado coal into a firebox that consumed fuel like a dragon. The thin mountain air should have strangled the fire, should have robbed the boiler of the oxygen needed to generate 190 pounds of pressure per square inch. But the draft system roared, sucking air through the grates with a violence that modern turbocharged diesels would recognize, even if they couldn't replicate it at altitude. Through the cab windows, engineer Thomas Riley watched the outside world tilt at angles that made passengers grip their armrests. 16-degree curves, so tight that a man standing at the locomotive's front couldn't see its rear, wrapped around cliff faces where a derailment meant a 1,000-foot tumble into nothing. The rails themselves spiked directly into wooden ties without the concrete ballast modern engineers consider essential, seemed to shift and breathe with the mountain's thermal expansion. This was the impossible-made routine, routes that modern railroad planners wouldn't approve for maintenance vehicles, let alone revenue service. Grades that would overheat contemporary diesel-electric locomotives before they climbed half a mile. Curves that would bind rigid-frame modern engines until their wheels screamed and derailed. Yet in 2025, this same route sees regular excursion service behind locomotives built when Calvin Coolidge occupied the White House. The descendants of Riley's mallet still climb grades that would leave modern power gasping, still navigate curves that would twist contemporary equipment into scrap metal, still operate in air so thin that diesel engines lose 30% of their power, while steam locomotives simply adjust their firing rate and continue working. The most decisive contradiction in railroad engineering wasn't written in computerized dispatch systems or satellite navigation. It was forged in 1920s steel by engineers who understood that conquering mountains required machines as relentless as the geology they challenged. No electronic fuel injection, no turbochargers, no computer-controlled wheel slip systems, just articulated frames that bent where rigid machines broke, and steam power that breathed mountain air and turned it into motion. The rails still climb toward Cumbres Pass today, unchanged since the 1920s. Modern freight trains detour hundreds of miles to avoid them. Tourist railways advertise them as death-defying adventures. But the old steam. Locomotives? They just call it Tuesday? Sarah Chen stood beside the disabled GE ES44AC locomotive, its 4,400 horsepower diesel engine ticking as it cooled in the mountain air of Monarch Pass. The massive machine, capable of hauling mile-long freight, consists across Nebraska flatlands, sat lifeless 3 miles into a demonstration run that railroad executives had sworn would prove modern technology could handle historic mountain routes. Coolant temperature redlined at 9,200 feet, Chen said, reading fault codes from her diagnostic tablet. Her supervisor, Frank Delgado, who'd spent 40 years in railroad operations, shook his head with the weary resignation of a man who'd seen this movie before. The numbers told a story that marketing brochures never mentioned. At sea level, the ES44AC's turbocharged V16 engine produced its rated power through precisely controlled combustion. But for every 1,000 feet of elevation, the air density dropped roughly 3%. At 10,000 feet, the turbocharger was force-feeding air that contained 30% less oxygen into cylinders that still tried to burn the same amount of fuel. The result was incomplete combustion, excessive exhaust temperatures, and cooling systems overwhelmed by heat they were never designed to reject at altitude. The locomotive's computer had done exactly what it was programmed to do, shut down before catastrophic engine damage occurred. "Third demonstration attempt this year," Delgado muttered, watching the wrecker being dispatched from the valley below. Last month it was the AC 6000 CW. Before that, the SD70 MAC. Different manufacturers, same result. Modern diesels can't sustain power at altitude. Chen pulled up specifications on her tablet, comparing the failed modern locomotive to historical data from the 1920s narrow-gauge operations. The contrast was startling. Where the ES44AC produced 6.1 horsepower per ton of locomotive weight at sea level, but barely 4 horsepower per ton at altitude, the old steam locomotives had actually gained mechanical advantage as they climbed. Steam engines didn't breathe air for combustion, they breathed it for draft, pulling oxygen through their fireboxes to sustain coal combustion. The lower atmospheric pressure at altitude actually improved draft efficiency, creating stronger draw through the grates. Firemen learned to adjust their firing techniques, but the basic physics worked in steam's favor. The grades presented their own challenges. The demonstration route featured sustained 3.5% climbs, relatively modest by mountain railroad standards, but brutal for modern power. Diesel-electric locomotives generated electricity through traction alternators that struggled with continuous heavy loads. Electrical components overheated, traction motors exceeded their thermal limits, computer systems initiated protective shutdowns. "Here's what kills me," Delgado said, pointing to a historical photograph on his phone. "This exact route, 1924 daily freight service with locomotives that weighed less than half what this beast does. No breakdowns, no overheating, no computer warnings, just steam and steel doing what they were built to do." The wrecker arrived 3 hours later, its diesel engine laboring audibly in the thin air as it dragged the disabled ES44AC back down to breathable altitude. The railroad's marketing department would quietly cancel further demonstration runs. The old steam locomotives, operating as tourist attractions on even steeper grades, would continue their daily climbs without electronic assistance or engineering explanations about why modern technology couldn't match what 1920s metalwork accomplished routinely. The rail inspector's transit showed what track geometry databases already confirmed. The curve entering Dead Horse Gulch exceeded 16 degrees, a radius so tight that modern railroad standards prohibited anything sharper than 10. Frank Delgado held the plans that illustrated why this section of track represented an engineering impossibility that somehow still functioned. Standard railroad practice specified that curve radius should accommodate the longest rigid wheelbase in the service. Modern freight locomotives measured 70 feet from front coupler to rear, with trucks spaced to distribute weight across that length. Their rigid frames demanded gentle curves, the kind that swept across broad valleys and followed river grades rather than climbing mountainsides. The Dead Horse curve measured 143 feet in radius, wrapping around a granite outcropping while climbing at 4%. Any modern locomotive attempting it would bind its trucks against the rails, creating friction that would either stall the engine or lift wheels off the inside rail until the whole consist derailed down the slope. "Conventional engineering says this track shouldn't exist," Delgado explained to Sarah Chen as they examined the curve's approach. "The clearance between equipment and rock face is sometimes measured in inches. The rail can't. The banking of the outside rail exceeds modern standards. The whole thing violates FRA regulations that were written specifically because curves like this killed people." Yet the old mallet locomotives navigated it daily during their revenue service years, and tourist operations still ran it without incident. The secret lay in articulation, a concept so elegantly simple that its engineering brilliance became invisible. Traditional locomotives mounted all driving wheels on a single rigid frame, creating impressive mechanical strength but dismal flexibility. The mallet design split the locomotive into two independent engines, connected by a pivot joint that allowed the front engine to swing 30 degrees relative to the rear while maintaining steam delivery through flexible pipes. On straight track, both engines aligned and worked in unison, delivering combined tractive effort that could move mountain freight consists. But entering a curve, the front engine pivoted like a compass needle, its drivers settling into the arc while the rear engine's frame followed on its own trajectory. The locomotive literally bent in the middle, conforming to curvature that would snap a rigid frame. The wheel arrangement mattered enormously. The front engine carried smaller driving wheels, typically 40 inches in diameter, that could navigate tighter radii without binding. The rear engine used larger 50-inch drivers optimized for pulling power on straighter sections. Together, they created a machine that could slither through serpentine track while generating the raw force needed to climb grades that would stop modern power cold. Chen measured the Dead Horse curve's super elevation, the difference in height between inside and outside rails, 6 inches over standard gauge track, creating a bank angle that would cause modern equipment's center of gravity to shift dangerously. But the mallet's low-slung boiler and heavy frame sat so low that the same super-elevation actually improved stability, pressing the drivers harder against the high rail exactly where traction was needed most. The track itself bore witness to engineering from an era when maintenance meant skilled labor rather than computer-controlled machinery. Wooden ties, some original to the 1920s, showed wear patterns where articulated locomotives had flexed through curves for decades. The rail itself, 90-pound-per-yard iron that modern standards would reject as inadequate, had been laid with joints precisely positioned to avoid curves, minimizing the shock loads that could spread track under heavy tonnage. "Modern standards say this is unsafe," Delgado concluded, watching a tourist train's mallet ease through the curve with the mechanical grace of a steel serpent. But unsafe and impossible aren't the same thing. The old builders knew that. They built for conditions, not regulations. Ephraim Shea never intended to revolutionize mountain railroading when he patented his geared locomotive in 1880, but his Michigan logging operation faced grades that conventional locomotives simply couldn't climb. The solution he engineered, mounting the drivetrain on the side of the boiler and using geared reduction to multiply torque, would influence every mountain locomotive built for the next 50 years. By 1920, the principles Shea established had evolved and into sophisticated articulated designs that combined his torque multiplication concepts with the flexible frame geometry that mountain operations demanded. Engineers like Anatole Mallet in France and William Buchanan in America understood that conquering altitude required rethinking fundamental assumptions about locomotive design. Traditional locomotive engineering prioritized speed and efficiency across relatively level terrain. Direct drive from cylinders to driving wheels maximized horsepower translation to rail speed, perfect for moving freight across prairie or coastal plains. But those same design choices became fatal limitations on mountain grades where adhesion, the grip between wheel and rail, mattered more than raw power. Frank Delgado kept copies of the original engineering specifications for the Rio Grande Southern's mallet fleet, documents that revealed the obsessive attention to weight distribution that separated successful mountain power from expensive failures. Every component location was calculated to maximize downward force on driving wheels while maintaining the flexibility needed for extreme curves. The boiler sat low, its centerline barely 5 feet above the rails, creating a center of gravity that improved stability on grades where top-heavy locomotives would tip on the super-elevated curves. The water tanks mounted not on the tender but integrated into the locomotive frame itself, placing liquid weight directly over drivers where it provided maximum adhesion. Weight distribution followed principles that modern engineers would recognize as sophisticated traction control, though achieved through mechanical design rather than electronic intervention. The front engine carried 4% of total locomotive weight, enough to pull around curves without binding but light enough to allow the truck to pivot freely. The rear engine bore 6%, pressing those larger drivers against climbing rails with force that multiplied available traction. Buchanan's specifications for the DNRGW's K-class mallets showed calculation precision that rivaled modern computer modeling. He positioned cylinder bore and stroke dimensions to deliver maximum starting tractive effort at low speeds, exactly where mountain climbing demanded power. At 10 miles per hour on a 4% grade, those locomotives produced pulling force equivalent to 80% of their total weight, a figure that modern diesels couldn't approach even at sea level. The detail that separated working mountain locomotives from museum pieces lived in components most passengers never saw. Suspension systems that allowed individual wheels to rise or fall 6 inches independently, maintaining contact with track whose alignment varied wildly over hand-laid mountain grades. Steam delivery systems with flexible joints that could articulate 30 degrees without leaking. Brake rigging that provided independent control to each truck, essential for descending grades where runaway trains meant disaster. Sarah Chen studied photographs of the construction crews who'd built these machines at Baldwin Locomotive Works in Philadelphia. Skilled metalworkers who shaped boilerplate with hammers and heat, creating riveted joints that would hold 200 psi for decades. Pattern makers who carved wooden forms for castings whose geometry couldn't be captured in the limited engineering drawings of the era. They were building for conditions that would kill conventional designs, Delgado observed, pointing to a photograph showing a completed mallet being tested on Baldwin's demonstration track. Every specification was written in the language of mountain operation: maximize adhesion, minimize rigid wheelbase, deliver torque at low speeds. Speed ratings didn't matter. These machines were built to climb, not sprint. The physics that doomed modern diesel locomotives at altitude became steam power's unexpected advantage, a thermodynamic reversal that Frank Delgado demonstrated using nothing more than a pressure gauge and basic atmospheric science. Diesel engines are air-breathing combustion systems, he explained to Sarah Chen as they stood beside the failed ES-44AC. Fuel injection happens in precisely metered quantities, but combustion quality depends entirely on oxygen availability. At 10,000 feet, atmospheric pressure drops to 10 psi compared to 14.7 at sea level. That's 30% less oxygen per cylinder charge. Modern turbochargers attempted to compensate by forcing more air volume into cylinders, but thermodynamic limits intervened. Compressing thin mountain air generated excessive heat that stressed cooling systems already struggling with altitude conditions. Intercoolers helped, but added complexity and weight. The fundamental problem remained. Diesel combustion needed oxygen density that mountain altitude simply didn't provide. Steam locomotives operated under completely different principles that turned altitude from liability to advantage. The firebox didn't breathe air for combustion, it breathed air for draft, the upward flow that pulled combustion gases through the fire and out the smokestack. Lower atmospheric pressure actually improved draft efficiency. Chen examined diagrams showing the steam locomotive's draft system, an elegant arrangement where exhaust steam from the cylinders blasted up through the smokestack, creating a vacuum that pulled fresh air through the firebox grates. At sea level, atmospheric pressure resisted this draw. At altitude, reduced atmospheric pressure meant less resistance, stronger draft, and more efficient combustion. "Watch what happens when we adjust firing rate," Delgado said, showing historical firing logs from mountain operations. Sea level operation used roughly 120 pounds of coal per hour to maintain pressure. Same locomotive at 10,000 feet used 110 pounds per hour for equivalent power output. The draft improvement was so significant that firemen actually had to moderate their coal delivery to avoid being overpressuring the boiler. The water consumption revealed similar advantages. Steam locomotives carried their own oxygen supply in the form of water molecules, H2O, that decomposed in the boiler into hydrogen and oxygen atoms that supported combustion far more efficiently than atmospheric air alone. The process wasn't perfect, but it provided combustion support that didn't degrade with altitude. Modern diesels suffered additional altitude penalties through their electrical generation systems. The traction alternators that converted mechanical power to electricity for driving motors operated at fixed speeds, producing voltage that varied with load. Heavy tug. Loads at altitude meant lower RPMs, reduced alternator output, and decreased power to traction motors exactly when locomotives needed maximum effort. Steam locomotives delivered mechanical power directly from cylinders to drivers through connecting rods and valve gear that never lost efficiency regardless of altitude. The relationship between steam pressure and cylinder force remained constant whether operating in Denver or Death Valley. Boiler pressure multiplied by piston area produced identical pushing force regardless of atmospheric conditions. The cooling advantages proved even more dramatic. Diesel engines rejected waste heat through radiators that depended on airflow and temperature differential between coolant and atmosphere. Mountain operations meant thin air provided poor cooling capacity, while sustained climbing generated maximum heat loads. The combination guaranteed overheating. Steam locomotives rejected waste heat by exhausting it directly to atmosphere as, well, steam. The exhaust blast that created draft for combustion simultaneously ejected waste heat into mountain air at supersonic velocities. No radiators to clog, no coolant to circulate, no thermal management systems to fail under stress. Here's the real advantage, Delgado concluded, pulling up thermal efficiency calculations. Modern diesels are theoretically 35% efficient at sea level, meaning 35% of fuel energy becomes mechanical work. At altitude, that drops to maybe 20%. Steam locomotives ran about 8% efficient everywhere. Altitude didn't change their thermodynamic limitations, but 8% of available power is the same whether you're at sea level or 12,000 feet. The steam engine's inefficiency became an advantage when diesel efficiency collapsed. Cumbres Pass demanded mechanical perfection from any machine attempting its crossing. The 64-mile route between Antonito, Colorado and Chama, New Mexico climbed from 7,888 feet to 10,000 feet through grades that averaged 4% and peaked at sustained sections of 4 or 5%, gradients where every percentage point represented exponentially increased resistance. Sarah Chen stood trackside as Locomotive 484, a 1925-built K-36 class Mikado, approached the final climb to the summit with 6 vintage passenger cars trailing behind. The machine's specifications seemed inadequate for the task, just 36,200 pounds of tractive effort compared to the ES-44AC's 183,000-pound rating. Yet where modern power had failed, the steam locomotive would succeed. The difference revealed itself in physics that transcended simple horsepower comparisons. The diesel's 183,000-pound tractive rating assumed sea-level operation with full electrical generation and optimal wheel adhesion. At altitude, with reduced oxygen density and overheating electrical components, actual available tractive effort had collapsed to barely 120,000 pounds, and that power couldn't be sustained for the extended duration that mountain climbing required. Locomotive 484 produced its rated 36,200 pounds at any altitude for as long as the crew could sustain firing rate and water supply. The steam admitted to cylinders at 200 psi pushed pistons with mechanical certainty that didn't degrade in thin air. The articulated frame distributed weight across 12 driving wheels, each pressing against the rail with force that prevented slipping even on grades slick with morning moisture. Frank Delgado monitored the locomotive's progress through the trackside observers posted at mile markers. 6 miles per hour average up the 4% section, he reported, translating radio calls into performance data. Steady steam pressure, no wheel slip, clean exhaust indicating efficient combustion. The machine is doing exactly what it was built to do. The curves presented opportunities to demonstrate articulated design advantages that rigid modern locomotives couldn't match. Entering a particularly severe S-curve that wrapped around Windy Point, a granite outcropping where track literally cantilevered over empty space. The locomotive's front engine pivoted smoothly while the rear drivers maintained their alignment on the straighter approach track. Chen measured lateral forces through accelerometers mounted to the passenger cars. Modern equipment on similar curves generated lateral accelerations that approached passenger comfort limits, but the articulated locomotive's flexibility actually reduced these forces. The front engine's independent truck absorbed curved geometry while the rear engine followed on its own trajectory, creating a smoother ride than rigid-frame locomotives could provide. The summit approach required maximum sustained effort, a 2-mile climb at continuous 4.5% grade through curves that never straightened enough to allow speed buildup. This was where diesel locomotives had consistently failed, where cooling systems couldn't reject heat fast enough, and electronic governors initiated protective shutdowns. Locomotive 484 clawed up the grade with mechanical relentlessness that made altitude irrelevant. The fireman maintained steady coal delivery, adjusting his shovel technique to account for the improved draft that mountain air provided. The engineer controlled speed through precise throttle and cutoff adjustments, allowing steam to expand in cylinders with efficiency that increased as boiler pressure remained stable. At the summit, the locomotive paused at the snow shed where crews traditionally stopped to check equipment and take water. Chen examined the driving wheels, expecting to find evidence of stress from the sustained climb. Instead, she found mechanisms operating within normal parameters. Bearings warm but not hot, tire surfaces smooth and unmarked, suspension components showing normal articulation wear. "What's the maintenance interval on these?" she asked Delgado, comparing the steam locomotive's apparent condition to the failed diesel cooling back in the valley. "Daily inspection, monthly component checks, annual teardown for bearing examination," he replied. "These machines run 6 days a week through summer season, making this exact climb twice daily. The design tolerates the abuse because it was built for abuse. No computers to crash, no sensors to fail, just steam and steel doing work that modern technology can't sustain." The descent proved equally revealing. where diesel-electric locomotives struggled with brake management on mountain grades, dynamic braking systems that generated electricity through traction motors acting as generators, the steam locomotive used pure mechanical braking supplemented by steam cylinder resistance. The engineer could open cylinder drains and allow back pressure to slow the train without touching the brake shoes, preserving friction materials for emergencies. "We just watched a 100-year-old locomotive do something that contemporary power can't manage," Chen concluded, reviewing her data as 484 began its descent toward Chama. Not because the old design was better in absolute terms, but because it was optimized for conditions that modern engineering assumed away. The economics of mountain railroading revealed truths that transcended simple performance comparisons between old and new technology. Frank Delgado's analysis of operating costs showed why steam locomotives continued serving routes that modern power couldn't reliably operate. A contemporary diesel-electric locomotive cost roughly $2.5 million purchased new, then required sophisticated maintenance infrastructure, diagnostic computers, specialized technicians, proprietary replacement parts sourced from manufacturers who controlled supply chains. Component failures meant expensive repairs and extended downtime, while parts shipped from distant facilities. The Cumbres and Toltec Scenic Railroad operated 5 steam locomotives on a maintenance budget that would barely support 2 modern diesels. The difference emerged from design philosophy. Steam locomotives were built for field maintenance using basic tools and readily available materials. Worn bearing surfaces could be machined in the railroad's own shop. Leaking boiler tubes were replaced using standard pipe stock. Failed components were rebuilt rather than replaced. "We manufacture about 30% of our replacement parts in-house," explained the railroad's master mechanic, showing Sarah Chen the machine shop, where craftsmen still practiced trades that dated to the steam era. "Valve stems, piston rings, crosshead shoes, we make them to original specifications using manual mills and lathes. Total cost is maybe 15% of buying modern equivalents, and we control quality." The parts that couldn't be manufactured locally came from a supply network that had evolved specifically to support heritage steam operations. Specialty foundries cast replacement cylinders and frames. Machine shops across the country maintained capabilities to rebuild components that mainstream manufacturing had abandoned decades ago. But the fundamental advantage wasn't economic, it was physical. Steam locomotives operated through principles that altitude couldn't compromise. They didn't require oxygen-rich air for combustion, didn't generate waste heat that exceeded cooling capacity at elevation, didn't depend on electronic systems that failed when atmospheric pressure dropped. Chen compiled her findings into a report that challenged assumptions about technological progress. Modern locomotive design optimizes for conditions that don't exist on mountain routes, she wrote. The electronic controls, computerized fuel injection, and electrical traction systems that dominate contemporary power all assume operation in environments where air density supports combustion, where cooling capacity matches heat generation, where maintenance infrastructure can support complex systems. Mountain routes violated every one of those assumptions. Thin air strangled combustion efficiency. Altitude limited cooling capacity. Remote locations made complex maintenance impractical. The conditions that modern locomotives were optimized for simply didn't exist above 9,000 feet on sustained grades through impossible curves. Delgado watched Locomotive 484 prepare for another day's climb to Cumbres Pass, its crew performing inspections that hadn't changed substantially since the machine was built. "We're not operating these locomotives because of nostalgia," he said. "We're operating them because nothing built in the last 50 years can reliably do what they do daily. The engineering that seemed obsolete turned out to be optimized for conditions that modern design assumed away." The rails climbing into the Colorado mountains stood as proof that technological progress wasn't linear. Sometimes the solution to impossible conditions required returning to principles that predated electronic sophistication. Sometimes the oldest answer was the only answer that worked. The steam whistle echoed across Cumbres Pass as 484 began its climb, the same sound that had announced mountain conquest for a century. Modern power sat silent in the valley below, defeated by altitude and physics. But the iron that refused obsolescence continued its ancient work, proving daily that some engineering challenges demanded solutions forged in an era when impossible simply meant not yet achieved.